Bye, bro. Hey everyone, I just did a video on how encryption works. And in that video, I realized I said the term XOR a whole bunch of times. So in this video, I want to quickly review what is XOR. And it's really all to do when we're dealing with binary. So we have some zeros and ones, and we're going to do some interaction with some other zeros and ones. This could be individual bits. It could be an array of bits. But the whole point is we're doing some operations between two sequences of bits to get another sequence of bits. And when we think of this, it's very common that 1 is true, 0 is false. Remembering binary, it can only be 1 or 0. It's one of those two states. And so we perform some action on 2 bits that gives us another bit. And those actions, we commonly think of and or. So I'm going to review those first. And we use and or all the time in life. I could think of, we'll start with and. So if we think of the and operation, and I can think about, we have the idea of a truth table. And I can think of, well, there's values coming in. So one set of values could be 0 and 1. And the other set of values could be 0 and 1. Then the result is if we AND those values together. So if I AND those values together, well, if it's 0 and 0, the result is 0. So if I'm doing some truth, is if this is false and this is false, well, the result is false. If one of them is true, but the other is false, well, at the end, I need both to be true. So it's still false. This one is false and this one is true, it's still false. But if both of them are true, then the result is true. I could say, for example, hey, if you tidy your room and take out the trash, then you can have a candy bar. So I can think that's an and. Both inputs have to be true to get a true output. We also commonly think of OR. So we'll have the truth table for OR as well. And once again, we'll have those same 2 options coming in. And this time the idea is if one of them is true. So it could be, hey, if you eat your vegetables or you have an applesauce, then you can have dessert. Now, as long as one of those things is true, then you get dessert. If you ate your vegetables and an applesauce, Well, you still did one of them, so you still get a dessert. So here the result comes out as, well, okay, if both are false, you don't eat the vegetables or the applesauce, well, it's false. You don't get anything. But now, if one of them is true, you've eaten your vegetables, or you didn't eat the vegetables, but you ate the applesauce, it's true. If you ate both, hey, it's still good. It's one of them has to be true, or they could both be true. So if or, as long as one of them or both are true, then the output of that is true. Then we get to XOR. So this is exclusive OR, and that's really the big deal, and it kind of gives you the hint of what's going to come out of this anyway. If it's exclusive OR, it has to only one of them be true. They can't both be false, they can't both be true. So with XOR, exclusive OR, and in my pictures I drew in the encryption video, I used this sign. So we have the same truth table again, and you probably can already guess what the output of this is going to be. If they're both false, well then the output is false. If one is true, then it's true. If this is false but this is true, it's true. But if they're both true, then it's false. And that's the big deal with exclusive OR. It's exclusively OR. It cannot be both of them are true. So that's where it's different from the regular OR. It's just that exclusive relationship. And this is extremely powerful in many things when we think of computers, but what I used was encryption. Because with encryption, the whole point is when I do an exclusive OR, if I run the exclusive OR again on the result, it puts me back to the original state, which is a really powerful thing. The other nice thing about exclusive OR is it will keep our result within a certain size. It's never going to overflow. It's never going to underflow. It will keep it in the exact size because I'm only ever I can never have 1, 1 come out at 1. So it's always going to keep me within a certain size. So if I took my example of my encryption, if I had some plain binary and it was just 1, 0, 0, 1. And then remember we had our encryption function, we had a key. The key is what made the encryption function come out with some unique sequence that looked random, but it's actually not. It's based on an algorithm, it's based on using our key and a certain round key. So we had our encryption algorithm using our key, and that spat out some binary. So let's say 1, 0, 1, 0. So the ciphertext would be the output of that. So if we take our encrypted values, so our ciphertext, so exclusive OR of 1 and 1, let's write in that exclusive OR. So what we're doing is an exclusive OR on these values. So 1 and 1, well, that's 0. 0, 0, that's 0. 1 and 0, that's 1. 1 and 0, that's 1. So that would have been our ciphertext. So we had the output of the encryption and our plain text, we XORed them to get our ciphertext. But now when I receive the ciphertext and I know the key, we have a symmetric, a shared key, I don't actually have to use a different algorithm to decrypt. I just run the same encryption algorithm, but instead of XORing the output of the encryption with the plain text, I now XOR the ciphertext with the output of the encryption. So it's the same encryption. One time I'm XORing it with the plain text, and then I just run it again with the cipher. And if I follow through this XOR, so 1 and 0, XOR is 1. 0 and 0 is 0. 1 and 1, well, that's 0. 1 and 0 is 1. And as you can see, we're back to our original message. And so that's why the XOR is so nice, that it essentially enables us to reverse by just running the operation again. That's why it's so useful. I guess when I'm talking about the most common things you might see, I should quickly mention NOT as well. NOT just operates on a single binary. So I have some binary over 0 or 1, and not just flips it. So the not would just say, well, 0 becomes 1, 1 becomes 0. So just when you think about all the different options, just that's another common one you'll see. And that was it. I just wanted to really quickly go over really what that XOR meant. And again, why it's so powerful for keeping some operation within a fixed size. But also that if I run an XOR and then I run the XOR again, it will actually get me back to that original value, which is why it's so useful when we think about encryption and security. As always, I hope that was useful, and I'll see you on the next video.
Hello everyone, in this tutorial video I'm going to explain the XOR operator or the exclusive OR operator. But before that, please support this channel by clicking on the subscribe button and hit also the notification bell so that you will be notified with all the new videos that I'm going to upload in this channel. And so like I said a while ago, I'm going to explain here in this tutorial video the XOR operator or the exclusive OR operator. Basically, this will return true if and only if one condition is true. There should be only one condition that is true. So meaning to say, if you have many conditions, only one of those conditions is true, then the result is true. If there are two conditions that are true, then it will give you a false result. And if you have all conditions that are false or true, then the result still is false. So exactly one only. And so to give an example of that, we have a program here. And so the result of this condition here, $A equal $D, A is 10 and $D is 10 also. Are they equal? Yes. So it is true. And then we have here $B less than equal $C. So B is 20 while C is 5. So less than equal 5. So the answer there is false. And so true, XOR, false, the answer here should be true. So the condition here as a whole, the result of this is true. And so therefore, if it is true, it will execute this. After which, it will go to 18 and then it will go to 22. So it will never execute the else because that is the false part. And so let's try to run that. I already ran it actually, so we just have to run it again. So as you can see, it's true. So true part here. So it executed this one. So there should be only one true. So let's say, for instance, I'm going to make this one as true, the second condition here. So for instance, I'm going to say B greater equals C. B is 20 while C is 5. So definitely the answer here is true. And so therefore, if we will run this, it should give us false. Why? Again, because the concept of the XOR is that there should only be one and exactly one condition that is true. Okay, so many conditions there, only one of those will be true, then the result is true. So if it is more than one where the condition is true, if you have two conditions that are true, then it will become false. So because there should be only be one true condition and the result will be true. And so therefore, with this program, this is the result of it if we will try to run it. So similarly, if the result is false, so if all are false, for instance this one, $A not equal $D, that's false. 10 not equal 10, that's false. And then this one, B, let's say less than equal C, so that's also false. So false and false, it will give you still false. Okay, so because there should be one true so that you will get a true result. Now, let us add another one so that we will see. This time we have 3. So for instance, I'm going to say $A greater or less than. I'm going to use less than, or let's say greater equal $C. So A is 10, greater equal C, which is 5. So the result of this is true. So there is only one true. There are 2 false. So the result should be true. So it should print true part here. So it will execute 17. There you go. So it's something like that. So once again, I'm going to make this one as true. So let's make this one as true. B greater than equal C. Yes, because B is 20 while C is only 5. So B is greater than C. So that is true. And so when we run it, it should give us false because, see? So the result there is false because there should only be one true, so that it will give us a true result. So as you can see, we have 3 conditions here. So that's how the XOR operator works. As simple as that.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, sum of all subset XOR totals. So this is an easy problem, but there is a solution to this problem that is pretty damn hard, I would say. So I'm going to go ahead and show you the probably intended solution that makes this an easy problem. It's not going to be like the most efficient, it's going to be exponential. And I'm also going to show you an optimal solution, which I will warn you is pretty mathematical. And I'll even admit to you that I actually wasn't able to come up with it by myself. I didn't know that an efficient solution actually existed for this problem until I skimmed the editorial. But I recognize that that editorial is pretty difficult to read. So if I can make it any easier for you to understand, I'm happy to do so. But let's get started with this problem. Kind of like yesterday's problem, it's all about the XOR binary operation. Basically, we're given an array of elements. I'll take the second example. It's a bit more interesting. 5, 1, 6. We want every single subset of these elements. Now, remember, subset is not the same as a subarray. If we were only talking about subarrays, then we'd have roughly n squared subarrays. But with subsets, the idea is different. We'll have about 2 to the power of n. And the reason for that is with a subset, we have a choice for every single element. We can either choose to include it or not include it. So if I just wanted to show you what every single subset from this looked like, I would do this. I'd say, okay, first time we include 5, and we can also skip 5. And then we can include 1, and then we can skip 1. We can include 6, we can skip 6 over here, and we can include 6 here, and of course skip it. Same thing over here. I'll just quickly draw it out here. We're at the second choice. We can either just wanted to show you what every single subset from this looked like, I would do this. I'd say, okay, first time we include 5, and we can also skip 5. And then we can include 1, and then we can skip 1. We can include 6, we can skip 6 over here, and we can include 6 here, and of course skip it. Same thing over here. I'll just quickly draw it out. Here we're at the second choice. We can either include 1, skip 1. Here we can either include 6, skip 6, and same exact decision down here. Now, if you take any one of these root to leaf paths, you will have a different subset. Even though the input elements could be duplicates, so like even though like two sets might have the exact same values, they're still technically different subsets. So if you count all of these, you're going to see we have, I think, 8, right? So the reason for that is we branch by 2 every single time. If you look at the height of this decision tree that I have, it's a height of 3. Therefore, we're going to get 2 to the power of 3. That's going to be 8. There's 8 different subsets that we can form. And if you look at one of them, it's an interesting one over here where we literally didn't include any element. So that actually does technically count as a subset. So that subset, in the context of this problem, which I guess I should talk about, for every single one of these subsets, we want to take all the elements and XOR them together, and then we'll get a result. So if we were to XOR, I think, these 3 together, we'd get something like this. Well, actually, let me start with the other one. If we were to XOR nothing together, like there's no elements to begin with, then obviously that's going to be 0. This one over here, where we have nothing but a single 6, 6 by itself is just going to be 6, right? This one over here, 6 and 1, if we were to XOR 6 and 1 together, what would we get? Well, in the binary representation, 1 looks like this, 6 I think looks like this. So if we XOR them together, I think we actually get 7. So for each of those, we're going to end up adding all of them up, and that's the result that we're trying to return. So for any given subset, XOR all the values, and then for that, get that total, and then add all those totals up. So we'll have 8 numbers. One of them is definitely going to be 0, and then we'll add all of them up, and that's what we're trying to return. So obviously, the brute force solution of this is recursive, and time complexity is going to be 2 to the power of n. To implement it in terms of code, obviously, we have to keep track of which position we're at in the input array. I'll use a parameter I for that. In terms of implementation, there are different ways that you can do it, but I think the easiest way definitely is to just keep track of the total of like the XOR values as we go. So like by the time we're here, the total is obviously 5. When we're here, we have nothing. The total is initially 0. When we're here, we are going to take the original total 5 and XOR it with 1, and then we'll have a new total, and then we'll kind of keep track of that total. And then by the time here we get to the base case, we'll know we're at the base case because we're at the end of the array, and then we can just return that total. And obviously, we're going to have 2 recursive calls because we're branching in 2 different directions. So I'm going to go ahead and code this one up first. So I like to have a little recursive function. I'm going to call it DFS. And like I said, we're going to have 2 parameters, I and just keeping track of the total. As you can imagine, the way we're going to call this DFS is starting at index 0 and having our total initially be 0. And then we're going to return the result of this. And we expect this to compute the total. So here, what I'm going to do is say, first of all, the base case you can imagine is going to be what I said. If I is the end, then let's just go ahead and return the total. Otherwise, we have 2 choices. I want to be very explicit with what we're doing here. We have one choice, include nums of I. In other words, we are going to make a recursive call. We're going to say DFS, go to index I plus 1. That's simple enough. Like we're going to do that regardless. But what's the total going to be? If we include this number, our new total is going to be total XORed with the number, nums of I. That's simple enough, but be very clear with what this function is actually doing. What this function is doing is it's returning the total of all subsets, including this number, every single subset. Because recursively, we're going to make that decision that I'm about to show you. We have the decision to include this number. We have the decision to not include nums of I. And that would look pretty similar. Let's go ahead and fix this. It'd be very similar. I'm sure you can modify it. It's just going to be removing this part of the code. So this is going to be returning the sum of all subsets that do include this number. This is going to be returning the sum of all subsets that don't include that number. And what we want to do is just total these 2 up and then return the result. So that's what I'm going to do. And I'm just going to, I guess, get rid of the comments now and just add these up in the same line because you probably can see what each of these means. Let's go ahead and run this. As you can see on the left, it works and supposedly it's pretty efficient, but there is a much more efficient solution to this problem that I'm about to show you right now. So I would buckle up because this is going to be a fun one, at least for me, because you guys know how much I love math and I know how much you guys don't like math, at least most of you. So this is mainly, I just want to say, combinatorics. It's kind of a branch of like discrete maths. It's like related to statistics and stuff like that. And it's also somewhat related to binary, obviously. The idea here is obviously we know for each of these numbers, like we're going to have 2 to the power of 3 subsets. So let's just continue with this example because it's small. So I'm just going to kind of draw like 4 little boxes here. These are going to be each of the subsets. We know that we can either include this or not include it. So half the subsets are going to include 5. Let's say that this row includes 5, and then this row does not include 5. So I'll just put a little red X here. You can suppose like 1 is included in half of them somewhere. They're just not like going to be nicely organized as these. So these have 5 included. These ones do not. Okay. I've also just gone ahead and shown you the binary representation of each of these. That's going to make our lives a little bit more easy. So suppose we just take 5 by itself, because we know 5 by itself is technically a subset as well. Let's take a look at it. There's a 0 here, there's a 1 here, there's a 0 here, and there's a 1 here. Now, there's going to be a bunch of leading zeros here. None of those are ever going to change, right? Because with XOR, we're never going to be adding a 1 somewhere where it doesn't exist. So now we're trying to look at an individual subset, and we're trying to really understand what an individual subset could possibly look like. We know for sure none of the subsets are going to have a 1-bit over here. I mean, we know that with 100% certainty, don't we? I think it's obvious why, because for us to have 1 as the result of an XOR operation, there has to be a 1 in the first place, right? And consider the other positions, like the other columns here. If there's a 1 in any of these rows, there's 100% going to be at least one subset where a 1 shows up. Because remember, we can take an individual element and just consider it as a subset. So even if we had 3 1s here, we'd have a subset. Even if I got rid of this element and there's 2 1s here, even though 1 XORed with 1 ends up as 0, well, we can still at least take this as an individual subset and this as an individual subset. So now I'm going to start looking at each of these positions, each of these 4 positions, and I've gone ahead and just moved that over there. Now I want to ask, among our 2 to the power of 3 subsets, how many of them are going to have a 1-bit set over here? Obviously 0, for reasons we just discussed. Now I'm actually going to go to this column because this one is a simple case. 2 to the power of 3, how many of these 8 subsets are going to have a 1-bit over here? You try to answer that question. Seriously, just look at this column. There's 2 zeros and there's a 1 here. This number is 6. We know 6 is going to be included in half the subsets, and half the subsets are not going to include 6. If 6 is included in a subset, regardless of which of the other elements are included, isn't it true that this 1 bit is always going to be set? Because 1 XORed with 0 is always going to be 1. You can do it 100 times, it's still going to be 1. So what I'm getting at is when there's only a single bit set in like a column, then half of the subsets, in other words, 2 to the power of 3 minus 1, half of the subsets are going to have this bit set. Okay, now's the part where it's going to get really interesting, and that is this. Suppose I have half the subsets where they look like this, where this bit is set, and I have half the subsets where this bit is not set. So I'm going to be focusing on this bit. So let's just draw a 0 and a 1. Half of them are 0, half of them are 1. Now suppose I introduced here a new value. I introduce very intentionally this value 0, 0, and a 0 over here, but here I'm putting a 1. Suppose I did that. So obviously we have taken our subsets and doubled them, right? We've multiplied it by 2 because now this subset is going to be included in half and not included in half of them. Okay, so we know originally our ratio of 0 to 1s in this bit was 50-50, right? So now I'm going to take this new value and I'm going to XOR it with everything we have. If I take this 1 and I XOR it with a 0, because remember, half those subsets are going to have a 0 here. If I XOR 1 with 0, what do I get? I flip it, of course, right? I flip it and it turns into a 1. Now I take this and I XOR it with the other half of those subsets that we had. So obviously in this particular position, it's going to be 1 XORed with 1. What does that result in? It results in a 0. It gets flipped. So the ratio, what I'm getting at, is going to stay 50-50 because half of them had a 0 in this spot. If I XOR 1 with 0, it turns into 1. And half of them had a 1 in this spot. If I XOR 1 with 1, I get 0. So it looks to me like if we have 2 1s in a particular column, we still have half the subsets where this bit is going to be set and half the subsets where they're not going to be set. And obviously, if I introduce another one, if I had 3 1s here, then I'm going to do the exact same thing. I'm going to set all of them that have a 0 to be a 1 and all of them that have a 1 to be a 0. So in other words, if there is a bit set in any column, half of the total set of subsets is going to include a 1. Now I'm going to get very, very concrete and go through this example by hand, and there won't be a single doubt in your mind why the solution I'm about to show you is going to work. So what we've learned is that this column, of course, half of the subsets are going to be a 1. And obviously we know that since there's a 1 set somewhere in this column, half of the subsets are going to be 1 here as well, 2 to the power of 3 minus 1, same thing over here. So if half of the subsets have a 1 in this spot, then isn't it fair to say that this value is going to be multiplied by the value below it? Like this here alone, like this by itself, just kind of ignoring these two for a second, this by itself is the value 4. Like that's what this bit represents. And it shows up 2 to the power of 3 minus 1 times. In other words, it shows up 2 to the power of 2, which is 4. It shows up 4 times. This bit is going to show up 4 times among these 8 subsets. So we can say this, which is the number 4, multiplied by 4. What about this? Well, it represents the number 2. That bit is going to show up 4 times. So we take 2 times 4. And same thing over here. This represents 1. It shows up 4 times. 4 different subsets are going to include that value. So we're going to say 1 times 4. So now we can just total these up. We're not obviously looking at each individual subset and looking at what that number represents. We're just saying that this bit is going to show up, however many times, and we're adding it up that many times. So if we were to total each of these up, it's going to be 16, 8, and 4. If you add all those up, I think you get something like 24. But obviously you can see that here, a good way to simplify this would actually be to take the number itself. Like we have 4, 2, and 1. Why not just take that number, the sum of that 7, which is what like this represents, and multiply that by 2 to the power of 3 minus 1, which is of course 4, which is of course 28. Now, if this doesn't make sense, let me just quickly draw 8 random subsets that don't necessarily match the result of this, but they're consistent with what I said down here. So what I'm saying is that there's going to be 8 rows and half of them are going to have this 1-bit set. So let's just assume it looks like this. So I'm going to put it like that. I'm also going to say that half of them are going to have this bit set. It could be overlapping with this or not. So let's say 0, 1, 0, 1, 0, 1, 0, 1. And I guess since we put all zeros here, we have to put these ones up here. So let's just put those 4 ones here and then zeros here. So this is consistent with the logic over here, even though these are definitely not the 8 subsets that are going to be generated by this, but the sum of these is still going to be 28. Because to total these 8 subsets up is literally just taking this, which is 2 times 4, taking this, which is 4 times 4, taking this, which is 4 times 1. Okay, now let's finally get into the solution. How does all of this help us? Well, all we have to do is find which bits are actually set in at least one of the numbers, and then we can take that, kind of what I drawn here, take this and then multiply it by 2 to the power of 3 minus 1, Or you could also say left shift it by n minus 1, where n is the number of values that we had, which in this problem was 3, because these are the 3 numbers. Now, how exactly do we find these? Like, how do we know which bits are actually set? You could obviously just, loop over each number. The easiest way, though, is just to logic or bitwise or these numbers together, because we just want to know that it shows up in at least one of the numbers. So if we take every single input number, or it together, we will get this. And then this itself will be multiplied by 2 to the power of n minus 1, or you could shift it to the left by n minus 1. Obviously, the time complexity of this is just going to be big O of n, as you'll see in a second. Okay, so all that work to code up a very simple solution, actually. So we'll say this is our result so far, and the first phase is just going to be going through every number and ORing it together. So result is going to be ORed with that number. So now we have all the bits that happen to be set. With those bits, we just want to say multiply them by 2 to the power of length of nums minus 1. I don't think I need these outer parentheses. And for what it's worth, this is equivalent to this shifted to the left by length of nums minus 1. I think here we would probably need parentheses. I just think that this is slightly more confusing because I think multiplication kind of really does explain exactly what's going on. So I'll go ahead and run it. As you can see on the left, it works, and I guess it is a bit more efficient. If you're preparing for coding interviews, check out leetcode.io. Thanks for watching, and I'll see you soon.
Welcome to this presentation on problem titled Sum of all subsets or totals. In this session, ask us to compute the array nums with elements 1 and 3. Its subsets are the empty sets 1, 3, and 1, 3. The sort values of these subsets are 0, 1, 3, and 2 respectively. Summing this, we get the total sort sum as 6. Our approach is based on depth-first search using backtracking. For every element in the array, we have two choices: include it in the current subset and sort it with the current total, or exclude it. By exploring all possible combinations recursively, we can cover all subsets and calculate their sort values. Let's now look at the C++ implementation. The subset sort sum function serves as the entry point and initializes the recursion by calling the DFS function with the array starting index 0 and an initial sort value of 0. In the DFS function, we define the base case. If the current index equals the array size, we have completed forming a subset and return its sort value. We then branch into two recursive calls, one where the current element is included by applying sort, and another where the element is skipped. The results of both branches are summed and returned to build the final total.
Hello everyone, so in this video, let us talk about an easy problem from LeetCode. The problem name is sum of all subsets XOR total. So the problem statement goes like this, that the XOR total of any array is defined as the bitwise XOR of all its elements. Okay. Now what your overall problem statement is that for a given array, you have to find out the sum of the XOR totals of all the subset of that particular array. So you just have to find the subset, all the subset for that given array. And then among all the subsets, you have to find out the XOR total. Okay, from the subsets, you will get like separate arrays. Then you will just find out the XOR of all the elements in that particular subset and just add a total of all of them and just return the answer. That's it. Now, because as you can see in the constraint, n is pretty small. Okay, like the total number of the total length of the nums is 12 only. So you can just do it in a very brute force way. Just find out all the different subsets and also for every subset, find out its XOR.
Hello guys, welcome back to TechDose, and in this video we will look at some of all the subset XOR totals, which is from LeetCode number 1863. We will be looking at two techniques. One will be involving recursion and backtracking, and another one will be involving bit manipulation with maths. The proof of this second technique will be shown at the end of the video, so stay tuned till the end. Let's now read the problem statement. In this case, the XOR total of an array is defined as the bitwise XOR of all its elements, or 0 if the array is empty. For example, the XOR total of an array 256 is 2 XOR 5 XOR 6, which is 1. Given the array nums, return the sum of all the XOR totals of every subset of nums. Note that the subset with the same element should be counted multiple times. An array A is a subset of an array B if A can be obtained from B by deleting some, possibly 0 elements of B. Now, if you look at an example, like let's say the second example, then in this case, in order to generate all possible subset of these three items, you have two options to select or not select the given item, right? So with three items, you can have total 2 to the power 3 number of subset. And if you enumerate all the subsets, then it has already been given that you will have an empty set first, and then you can have only 5, 1, 6, 5, 1, 5, 6, 1, 6, and 5, 1, 6. Now, if you take the XOR of all these subsets, then the 5's XOR will be 5 because there is only a single item. 1 XOR will be 1, 6 XOR will be 6, 5 XOR 1 will be 5 is this, and 1 is this one, right? So if you take a XOR, it will be 4. So 5 XOR 1 is 4. Similarly, 5 XOR 6 will be 3, 1 XOR 6 will be 7, 5, 1, 6. All of them XORed will be 2. Add all the XOR values of all the subset, and then you get 28. And that is how this can be calculated, right? So this is the brute force approach by doing the enumeration of all the items. But if you look at the constraint, there are maximum 12 items. So if you write a 2 to the power n algorithm, because if you have two options for each item, then you will end up with 2 to the power n such combinations. Then this will boil down to 2 to the power of 12, which can be written as 4 times of 10 to the power of 3, where 2 to the power 10 is assumed to be 10 to the power of 3. This is way below your 10 to the power of 8, and definitely this is going to run well within 1 second, right? So even if you write the backtracking or the recursion algorithm, then this is going to pass. All the array elements are within the 32-bit integer. Actually, it is a very small number, 1 to 20, right? Now let's look at how to solve this by recursion. So simply, if I have an array having three items, let's say 4, 3, 5, I have already given the bit representation for all of them. Then I can generate all possible subsets. And in order to do that, I can make the recursion tree diagram simply. So I will start iterating from this first item, which is 4, and I will start with a XOR value of 0. I will keep a sum of all the XOR values of every subset, and it will be initialized to 0. Now I have an option to either not include this 4 into our subset or to include this 4. If I don't include this 4, my XOR value will remain to be 0 and I am at 3. If I select not to include this 3, then my XOR value remains to be 0 and I am at 5. If I decide not to include this 5, then my XOR value here will be 0, and so 0 will be added to the sum and it will still remain to be 0. Now I will come back to 5 and try to include this 5. So if you include this 5 XOR with 0 will be 5, so the XOR value here is 5. This is for subset which has only 5. So 5 will be added here and the sum value will become
Alright. Assalamualaikum.
5. Then you return back to 5, go back to 3. Now you try to include 3. If you try to include that, then 3 will be XORed with 0 and so the XOR value here will be 3. Now if you do not include this 5, then you reach to the end which only has 3 as the XOR value. This is for the subset which has only 3, and so 3 will be added and the total sum will reach to 8. Now you come back and try to include this 5. Now if you try to include 5, then you already have 3 as the XOR value. 5 will be XORed with 3. So if you XOR 5 with 3, you see that this is unset in 3, so it will be 1, this will be 1, this will be 0. So this value is 6. So you will have a 6 here. So 6 will be added to this and it will become 14. And now you will come back. So this 6 is for when 3 comma 5 both are included, right? Now you will come back, go back to 3 and go back to 4. Now you will try to include this 4. If you try to do that, 4 will be XORed with 0 and the XOR value will be 4. If you try not to include this 3, XOR will be 4. If you try not to include this 5, then the XOR will be 4. This is for the subset only having 4, and so 4 will be added here and this will become 18. And now you go back to 5. Now you try to include this 5. If you do that, then 5 will be XORed with this 4, XOR this 5 with 4. Only 1 will be remaining, right? And this is for the subset which has 4 comma 5. So only 1 was remaining, 1 will be added and this becomes 19. Now you go back to 5, go back to 3 and now you try to include this 3. If you try to include 3, then 3 will be XORed against 4. Okay? And once you do that, it will become 7. Now if you try not to include 5, then you reach to 7, which is for the subset 4 comma 3, and so 7 will get added here and this will lead to 26 value. Now you go back to 5 and try to include this 5. So 5 will be XORed against 7. You see 5 will be XORed against 7. So the value will be 2 here, which is for 4 comma 3 comma 5. And so 2 will be added to it and the value will become 28, right? And then you go back to 5, go back to 3, go back to 4 and you are done. So in this entire recursion approach, the sum value will be updated to 28 and that is our final result, right? So the total number of nodes in this tree will be 2 to the power of n, where the height of this tree is n. And since the height of the tree is n, due to the recursion call stack, your space complexity will be order of n and the time complexity will be 2 to the power of n, because at every node we are just doing constant operation which is taking the XOR, okay, taking the XOR with the current item, that's it, and making the 2 recursion calls. So this is the simple brute force approach which is going to pass definitely, right? Now you have seen the recursion tree diagram. Now let's try to understand how to solve this with an optimal bit manipulation with the math approach. Okay, so I will do the problem deduction here. You already know that let's say the array is 435, then I can enumerate all possible subsets and there will be 2 to the power 3 possible subsets for these 3 items which I have already written. Now I have to calculate the XOR value of all the subset. For an empty set it will be 0. For 4 it will be 4, 3, 5 it will be 3, 5. For this 4, 3 it will be 4 XORed with 3 which is 7, right? So accordingly I have calculated and I have already given the bit representation using 4 bit. Okay, Now the answer should be the sum of all the XOR values, which will be 28 in this case, which we have already seen, right? Now, if you look at any number, like let's say I show you this number 0110. In this case, this one is the first bit because the bit will be counted from right to left. This 0 is the 0th bit. This 1 is the first bit. This is the second bit, right? So here for this XOR 6, since 6 has a value 0110, so the first bit and the second bit are actually set. This is saying that the first bit is actually contributing to the final XOR sum value, and the second bit is also contributing to the final XOR sum value if you take the subset 3 comma 5. Okay, and that is how you got the 6, isn't it? So instead of adding all these values one by one, you can also say that in how many subsets this 0th bit is contributing, plus in how many subset the first bit is contributing, plus in how many subset the second bit is contributing, third bit is contributing, and so on till the maximum number.
Slow. Üçüncü derece satıda satıyor. Beş ve altı. Elbette oynayacağım. Yukarıda. Önce satırlarını sağlamış gerek. Satırlarını sağlamamış hani bunları ikkili eninchi darajasi bo'ladida, chunki bizda nechta element bo'lsa o'shani ikkinchi darajasi bo'yicha subset bo'ladi. O'sha bo'yicha for aylanib inchi keyin I plus birinchisi subsetlarni qanday generatsiya qilib olaman? Birinchi savol shu, buni subsetlarni qanday generatsiya qilaman? Nosta buni subsetlarni qanday generatsiya qilaman? What was where is it going? Doğru. Torta buluşturalım. Buradaki ikkili üçüncü derecesi satışı çıkıştıralım. 6 8 Paste the archivas. 9 yarım över książkę archiwie. No właśnie, dziękuję. NTH solution fish subject line function also mouse mouse contain program for each word as well. Oh, oh, okay. Oh, stars, subsets, yes, yes, subsets, subject line, whole, also, this, also, subjects, also, whole, subset also, Power grids also solutions can be automation and a similar area was many vehicles obtain uses for aggressive individuals create for income aviation traditional evidence of versatile and teaching performance subject and area variables. However, subject is special to the corporation or subject the element corporations. لو كان استخدام قانون سبتر هذا subject عشان طرق حلوة تشبيه get something source get something resolve mystery private education subjects horse subjects some subjects and the array non-staged array related. 네, 웃음이 쫄라를 90% odam qanday yechgan bu masalani? Salkam bir yarim soat. O'n to'qqiz millisekundga tushunga kursi ishlagan. Sekinlarga optimallashtirish kerak. Xudo xohlasa ertaga shu bilan sekinlarga optimallashtirishga harakat qilaman yoki просто bu masalani tushunmayapman. Lekin мощный masala ekan. Просто easy masala. Easy. No way. No way. I can breathe. Shunaqa gap. What the heck? Bu algoritm tushuntirmagan. Havasan qilib ketasanmi? Qo'sang bo'lmasini bog'lab qo'y. Qizlarga qo'shib ketmaysanmi? O'zimni qiynashim kerak. Просто kayfga sig'inishni yashashim uchun. Burgerni siz pashta targ'ib qiladigan texnologiya. Hali ertaga shu next optimallashtirishga harakat qilaman yoki просто skip qilib yana boshqa masala yechishga boshlayman. Просто easy masala. 90% odam yechgan. leetcode'da 4 million odam leetcode'da 4 million odam bo'lsa leetcode'da 4 million odam bo'ladigan bo'lsa o'shandan 90% 4 million 90% qancha bo'ladi? Bitta ko'ray dedi. طول نشتغل طول يعني короче, вечер в поезде nelerine to'qson foiz hammasi yechgan yoki gptdan urganmi bilmadim qanaqadan bo'lishi kerak